Hello, Algebra 2 students. Unit 5 was a difficult chore for us to get done for a couple of reasons. First off, the material was different from the stuff we'd been seeing before. Unit 5 is all about the quadratic equation and the parabolas that they graph. So it was a bit of a switching gears away from the linear equations that we'd been seeing the 2 units before that, and getting into the curved equation. So the quadratic was really the first of the new parent functions that we worked with. And another problem that kind of caused us a little bit of grief was the fact that Christmas kind of fell at a time that busted Unit 5 into 2 pieces. So we kind of took it in smaller chunks. This part was what we called Unit 5A, and it dealt particularly with the quadratic formula itself. But before we got to the formula, we introduced a topic that was going to be needed in order to work with the formula, and that was the idea of imaginary numbers. Okay, now specifically what we're saying here is that all values are broken down into 2 overlying categories. Those would be the real numbers, which are the regular number line that you've been working with from now all the way to the beginning of your educational days. And then there's what we call imaginary numbers. Now, we've never really had a cause to come up with an imaginary number or a definition for such a thing until now. And an imaginary number is the result of a negative value that is stuck underneath a radical that cannot be factored out by any other means. And that's important because it doesn't mean that every time you see a negative underneath a radical, the problem's always imaginary, because based upon the other math that's going on underneath the radical, or possibly by the presence of the type of radical that it is, like maybe a cube root or something like that, that negative might be able to come out from underneath that radical. It just depends. Okay, but once you've decided that the negative cannot be factored out, the only real way that we have to define what is happening is the presence of an imaginary number. Okay, now basically here's where we're at. Here's where the kind of the focus of an imaginary number comes from, and it is this. Okay, for everything that in mathematics there is an operation that undoes something. This is how we've been moving things from one side of the equal sign to the other all semester long, is that if you have something that is being added and you want to undo it and move it to the other side, we can always subtract it. Multiplying, we can undo with division, squares and square roots, and so on. And there's a lot of these things. Okay, but with squares, with radicals, something starts to happen. And of course, we know that anytime you take a value and square it, we're going to end up with a positive number. And that's just one of the very basics. A positive times a positive is positive, but a negative times a negative is also positive. So if you start off with a negative number and square it, and then decide, oh, I didn't want that squared, let me take the square root and get my value back, well, we end up with a positive value, even though we may have started off with a negative one. So we kind of learned that we have to consider both the positive and the negative of the same value, but it introduces the possibility that, hey, there should have been a negative underneath that radical to begin with in order to try to get the negative value back. So anyway, this is a small part of the explanation of that problem, and we don't really have the full explanation of it, but like a lot of other things in mathematics, when we can't explain something, we define it, and the square root of a negative value is defined as the imaginary value I. Okay, so we looked at how imaginary values can be factored out from underneath radicals, and more importantly, what we did is we came to a definition. I to the first is the square root of -1. So I squared is, of course, I times I. So that would be the square root of -1 times another square root of -1. Okay, those factor out together, and you end up with -1. Okay, similar thinking. I cubed is the negative of the square root of -1, and I to the fourth is +1. Okay, now there are obviously more exponents than 1 through 4 in the mathematical world, but these are the only 4 values of I that are needed, and you combine that with the fact that I is cyclical. So I to the 5th is the same as I to the 1st. I to the 6th is the same as I squared. I to the 7th is the same as I cubed, and so on. It repeats in a cycle of 4. So if you remember the first 4 values for I to the 1st, I squared, I I cubed and I to the fourth, then you have all of the values for I to any power that any ever happens to roll around. Okay. Now, if you get to those big values and you go, okay, I've got I to the 39th or I to the whatever, I don't know which value this lines up with. Okay, well, it's a division problem. If you take the power that you have and divide by 4, because the cycle runs in 4s, okay, whatever the remainder is will tell you where your I lines up with the first 4 values. In this case, we ended up with a remainder of 3. That means this lines up with I to the 3rd power, which is the negative of the square root of -1. Okay. Anyway, we refreshed our memories on the 5 laws of exponents. So very quickly, if you have two bases that are the same and are being multiplied, law 1 says to keep your base and add up your exponents. Law 2 says if you have two bases that are the same and are being divided, law 2 says to subtract the numerator's power minus the exponent's power. If you have a base that is being raised to an exponent and then raised to another exponent, law 3 tells us to multiply those two exponents together. If you have a base that has a negative exponent, okay, law 4 tells us that we can rid ourselves of the negative exponent by reciprocating the particular base that you have. In other words, taking it from the numerator of a fraction and moving it to the denominator, or if it's already in the denominator, then move it back to the numerator. If ever we end up with a value that is raised to the 0 power, law 5 tells us that the conversion of that value is the numeral 1. Okay, so the rest of this was looking at some examples, and the reason we went so heavy into the imaginary numbers is because the quadratic formula itself has a habit of producing some negative values. So let's take a look. Okay. Now, we got to the basics of quadratics, and of course an equation is quadratic if one of your variables is in the second dimension while the other variable is only in the first dimension. That's going to cause the graph to be kind of one long bend, and then the two legs of the graph run off to infinity. Okay, but more importantly, what the quadratic equation can do for us is it can tell us where the solutions for the equation are actually at. Now remember, if you only have one equation, only one curve in a graph at a time, solutions exist where the curve or the graph hits the x-axis. There's a lot of different synonyms that go along with that. Of course, it is solutions, x-intercepts, roots, zeros, x values, a lot of different way of asking the same thing, but it all means the same. Where does it cross the x-axis? So we have a formula seen at the bottom of the screen right now. That formula is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And where do you get all these values of a and b and c? Well, these are from the quadratic equation. Y equals a, x squared, plus b, x, plus c. Okay, and when you plug in those a's and b's and c's into the quadratic formula where it calls for, you end up with the possibility of having two different answers. We get two different answers because of the plus or minus that is built into the formula, meaning we have to work the equation one time considering the plus side of that, and one time working the negative side of that. Okay, but anyway, the rest of this was working through examples. If you struggled or think you may continue to struggle with the plugging in values into the quadratic formula, you might want to go back and watch this video and watch all the steps being worked out and all that kind of stuff, or possibly come in and ask for some help before or after school. Okay, now focusing particularly on the information underneath the radical, this is what we call the discriminant. And we call it the discriminant because this value, b squared minus 4ac, discriminates the type and number of solutions that an equation will end up having. Okay, so b squared minus 4ac, it has three possibilities. It may end up being a positive value, it may end up being a negative value, or it may not have any value at all. Okay, now based upon which of those three categories the discriminant fits into, that tells us how many solutions we will have and what type of solutions they will be. For example, let's say b squared minus 4ac, the discriminant is 0. Okay, if that is the case, then the number underneath the radical is 0. The square root of 0 is 0, which means our quadratic formula now says plus or minus 0. So what is the difference between adding 0 or subtracting 0? Obviously, there is no difference, so that will give us only one answer. Okay, only one solution, which means our parabola is just going to kind of barely nick the x-axis, just make contact with it on the way by as it turns and heads the opposite direction again. Okay, that will obviously be a real solution because, as we said, the only way to end up with an imaginary solution is to have a negative under a radical. Well, we no longer even have a radical if the denominator, or I'm sorry, if the discriminant is 0. So if the discriminant is 0, you will have one real solution. Now, if b squared minus 4ac, the discriminant, if it happens to be a positive number, well, that's going to give us the square root of a positive number. Okay, so since it did not zero out this time, that means that the plus or minus that is built into the formula is actually going to yield two different values, one from adding the square root of that number and one from subtracting it. So we will get two solutions if the discriminant is positive, and having a positive number under a radical is definitely a real value. It's a value that does exist somewhere on the number line. So if your discriminant is positive, you will have two real solutions. The third and final alternative or possibility for the discriminant is that it might yield a negative number. Now, if we do have a number underneath the radical, even if it is negative, that means that the plus or minus is still participating in the problem because you've got plus the square root of that number and minus the square root of that number. That's going to give you two different values. Okay. However, we have a negative underneath the radical. Okay, and then a negative underneath the radical is an imaginary number. Okay, now what that actually means to the graph is that there will be two solutions that will work with the problem. However, they are not on the x-axis as anticipated. Okay, so again, this is part of the failure that we acknowledge about our understanding in mathematics. We believe the solution should be on the x-axis, but here we have a situation where there are solutions, and they did not happen on the x-axis, so they're called imaginary. Okay, so understanding the value of the discriminant can tell us what type of solutions to anticipate and how many solutions to anticipate. Okay, but that is the value underneath the radical. B squared minus 4ac is called the discriminant. Okay, so that basically got us to Christmas break, and we had a Unit 5A test at that point. Then we came back after Christmas and really got into the depth of the polynomial that is the quadratic equation. Okay, so before we did that, we kind of detoured a little bit, made sure we understood a lot of the basic information about polynomials. So let's take a quick look at that real quick. Okay, now in short, what we said is, a definition of a polynomial. A polynomial is simply a series of terms that is being added or subtracted together. Okay, now that is the broad, all-encompassing term, polynomial. Now, polynomials can be broken down into smaller subgroups. Okay, and some of those subgroups would be like monomial. Okay, the prefix mono means one. So we are talking about a polynomial that has only one term. So that would be a term that is not being added or subtracted to anything else. Binomial is, of course, two terms that are being added or subtracted to each other. Then we have the term trinomial, of course, meaning three. We have three terms being added or subtracted to each other. As you get larger than a trinomial, there aren't really any specific terms that go along with those guys, so they are just called generically polynomials, and you can identify how many terms they have, such as a 4-term polynomial, a 5-term polynomial, or so on. Now, one of the terms that we've also come across this year and has been useful several times, we'd already seen it at this point in time when we were talking about asymptotes, is the idea of a degree of a polynomial. The degree, or what is sometimes called the order of a polynomial, is a word that describes what is the highest power that this polynomial has to offer. And we needed to know those things when we were looking at asymptotes, the highest power of the numerator and the highest power of the denominator, and so on. Okay, so that was basically it. Now, we went straight into multiplication of polynomials. We did not spend any time talking about addition or subtraction of polynomials, because in all honesty, that is very, very low level to add or subtract polynomials. You have to have like terms, and of course, like terms means you have the same variable, the same exponent, and if there are denominators, then you have the same denominator as well. Okay, so adding and subtracting is kind of a no-brainer. Same variable, same power, same denominator. Multiplication and division of polynomials is a little bit more tricky, and we were going to need bits and pieces of these skills moving into factoring, which was coming very soon. We stopped to take a look at it. Of course, multiplication of polynomials brings the distributive property largely into play. And one of the first things that we did is we kind of dispensed with the old junior high term of FOIL. Many of you learned to multiply two polynomials together by the FOIL method, where FOIL, from the word FOIL, is an acronym. It stood for first, outer, inner, last, and it would apply at a problem like you're looking at here at the bottom of the screen. Now you multiply the two first terms, the two outer terms, the two inner terms, and the two last terms, and that gives you the distribution of multiplying these two binomials together. The problem arose with a problem like this one that you're seeing in the center of the screen now. If you try to apply the FOIL method to something like this, you can see that there are a couple of bridges that are being built there that are not covered by the FOIL method. Okay, this is why high school teachers lobby against junior high teachers teaching you things like FOIL, because it does not cover everything that you're going to see. It works great for them in junior high, not so well for us in high school. Okay, so what we tend to do now is instead of FOIL, okay, what you need to remember is that if you have anything multiplying times anything else, just simply remember that everything from the polynomial on the left is going to have to multiply by everything in the polynomial on the right. Okay, and an easy way to remember how many terms you're going to end up with at the end of that distribution is however many terms you have from the polynomial on the left and how many ever terms you have from the polynomial on the right. Multiply those two numbers together, and that will tell you your overall numbers you should expect. So in the case of the polynomial you're looking at right now, 2 terms on the left, 3 terms on the right, 2 times 3 is 6. We should expect 6 terms from that distribution, and that's why you're looking at 6 bridges right now. Okay, so we worked through some examples together, but that is basic multiplication of polynomials. Now, when we say that you're going to end up with a certain number of terms, okay, that does not mean that some of those terms may not combine. Like, for example, you're looking at a binomial being squared, so that's 2 terms times 2 other terms. So as you can see, you end up with 4 bridges, 4 terms, but 2 of them are like terms, 10x to the first and 10x to the first. Okay, x to the first can add together with other x to the first to make 20 of them. Okay. So anyway, the problems can get bigger and bigger. It just means you have more and more bridges, and that's going to bring us bigger and bigger answers. Okay, so multiplication, not too bad. Now, there's actually 2 different methods of division that we looked at. One of them was long division, one of them was synthetic. Okay, long division proved to not be anybody's favorite. Okay, even though it is something that you have done in the past, we were just applying polynomials to it. So what we did is we took a basic look at the structure of long division. Now, we took it step by step as we went through in the notes. I'm not taking it step by step now. So if you struggled with the long division, you might want to go back and watch that video and see these problems worked out one step at a time. Okay, but the basic idea was the same. You figure out what goes on top to multiply times your divisor on the left. The result of that multiplication gets written down underneath your values, and then you subtract coming down the columns. And after you reach the point where your last number has been dropped down out of the dividend, then that ends up being your remainder, and your remainder goes over your divisor. So in this case, the problem, or the division went in 14 times, so that's our whole number. We ended up with a remainder of 3 over the divisor 4, 14 and 3/4. Now the same idea also applies with trying to divide when polynomials were involved. It's just a little bit of a different structure. Since we have more than one term with the polynomials, okay, we got, like in this case, a binomial as our divisor. That means that you have two terms that are trying to divide in. Well, two terms trying to divide in, first off, needs two terms worth of space to actually divide in. Okay, so we may not be putting a value over the leftmost term in the dividend. Okay, and when you figure out what number you're going to multiply by, the distributive property applies. Okay, so whatever number you put up top, it's going to have to multiply by, in this case, not just the x to the first of the divisor, but also the positive 1 of the divisor. Since it has to distribute and hit two terms, you're going to end up with two terms showing up underneath to then subtract coming down the columns. And again, these are worked out in great detail in the notes, step by step, all the way through. So you might want to go back and view that video if long division is a mystery to you. By the time you get down to the remainder, it works just the same as long division did. Whatever your remainder was, in this case it was a positive 2, goes over your divisor, which in this case was a x minus 2. That is your remainder. And keep in mind, as you work through the problem, your columns ought to all be matching up as far as powers are concerned. So notice all x cubes, x squareds, x to the firsts, and x to the zeros. They are all stacked with each other. If ever you get a mismatched exponent in one of those vertical rectangles that I just drew, then that means you have done something wrong. You need to get back and fix something. Now the synthetic division method, a lot of you preferred this one. The problem with synthetic division is that it is not all-encompassing. You can only use synthetic division if your divisor matches a very specific format. And that format is you must have only one variable. That variable must be in the first dimension, and then you can have plus or minus some constant. So if you have 1x to the first plus or minus some number, you can use synthetic division. Okay. Now, if you decide that synthetic division can be used, then it's a basic procedure in order to do it. And again, these are worked out in great detail in this lesson. So if you need more on synthetic division, go back and view the lesson. Anyway, what you do is you take the coefficients of the dividend. Okay, and in this case, that's a 2, a 3, and a -5, and you write them down. We take the constant from our divisor, we change its sign, and we put it in what we call the box. So in this case, the positive 1 of the divisor, we change its sign to a -1, and we put -1 in the box. The procedure was really very simple. You bring down the very first constant. So in this case, the 2 just drops down. Then it multiplies times the -1 in the box. So 2 times -1 is a -2. And we wrote that underneath the next value in the next column. So the -2 got written under the +3. Then we add them up, coming down the columns. +3 plus -2 is +1. Okay, anytime a value drops down below that line, we multiply it times the box. So +1 times -1 is -1, and we write it down in the next column over. So that -1 got written down underneath the -5, and then we add them up, coming down the columns. Okay, so -5 plus -1 was -6. Once you reach the last column, the problem is finished. Now, in order to structure your answer, we need to remember that the very last number written down was the remainder. remainder. Okay, so in this case it was a -6, and that goes over the divisor, which was x plus 1. The next term over, coming back from right to left, is your constant. So in this case, a positive 1. The next term over is your x to the first, which is the positive 2. And then you'd continue going leftward, okay, for the higher powers. Now, one thing you need to keep in mind for both the long division and the synthetic division method is by either method you are not allowed to skip any powers that are smaller than the degree. So in this case, the dividend starts off at x cubed, but it is missing its x squared term. It is missing its x to the first term. So when it comes time to set up the problem, we have to make sure that we put placeholder zeros in there to preserve the fact that that space did belong to those dimensions. So you cannot skip the second dimension right there just because it did not show up in the problem. You cannot skip the first dimension right there because it did not show up in the problem. They must be spaced out correctly. And again, these problems are worked out in great detail in the notes, so refer back to that if you need to. Okay, then that brought us to a discussion of factoring polynomials. Okay, so the basic factoring method is just the idea that it is possible that your terms in your polynomial may have something in common. And if they do have something in common, then they need to forfeit that thing right off the bat. Before we go into any of the other factoring methods or anything, always look for your polynomial having something in common with all of its terms. So in this particular case, we were looking at 6x squared plus 8x. They both have a 2 as a factor. They both have an x as a factor. So we would force the terms to give up the 2 and the x, and then we would basically see what is left over after each of those terms has given up the 2x. Okay, so that had to happen absolutely first before any other thing could be done. Okay, now particularly we were interested in trinomials because we were in the middle of a unit talking about the quadratic, which is a trinomial. Now, when your a term is a positive 1, this is the best case scenario that we can hope for. We want 1x squared plus something to do with x plus some constant. Okay, and the procedure is really very simply this. We would multiply together, okay, we want two factors that are going to multiply together to equal whatever a times c is, and at the same time that those two factors can add and subtract to equal the b term. Okay, so for example, in the problem that you're looking at there, you've got an a term of 1, which is what allows us to use this method, and then a c term of 8. Okay, well, the product of 1 and 8 is 8. So what we're looking for is two numbers that'll multiply together to equal 8, but those same two numbers add together to equal the b term, which in this case is a 6. So we took this 8, which was the product of 1 and 8, and we factored it to look at all the different factor pairs that 8 could be, and we found out that 8 could be a 1 and an 8, and it could be a 2 and a 4. And we want to add or subtract, we want these, either the 1 and the 8 or the 2 and the 4, to add or subtract to equal the 6. And obviously we can see we have the 2 and the 4. Okay, and after you discover your factors, you can actually go directly to the answer. Our trinomial is going to factor into two binomials, x plus or minus some number times x plus or minus some other number. And the two numbers are the factors that you just discovered, 2 and 4. Okay, now we've spent some time working on that, and we also discovered a definition somewhere along the way that if a trinomial will not factor, it is what we call a prime polynomial. Okay, now the real trick happened when a did not equal 1. Let's say you weren't talking about 1x squared plus or minus something to do with x plus or minus a constant. Maybe it's 2x squared like you're seeing here, or maybe it's negative 5x squared, something like that. Well, the idea still remains. We are still looking for, if we take our a and take our c and multiply them together, that gives us some product. We're going to take this product. We want two numbers that'll multiply together to equal that product, and at the same time those two values add or subtract to equal your b term. Okay, so in this particular case, it was a 2 and a -6, which gives us a -12. Okay, so we took the negative 12, we factored it all the different ways it could be factored. 1 times 12, 2 times 6, and 3 times 4. We want to add or subtract these groups of numbers to equal a positive 1, which was our b term. So clearly we could see that if we had a positive 4 and a negative 3, that would add or subtract to equal positive 1. And since we did want a negative 12, having one of these values positive and one of them negative is what worked. It made it work out perfectly. The catch is you could not go straight to the answer, straight to the binomials like you did if the a term was a 1. We had to do what some of you have come to know as the grouping method, or as we learned in class together, the boxing method. And what we did is we installed the a and the c term on one of the diagonals together. So from the problem, we had 2x squared and we had negative 6. Okay, so we put those on one diagonal together. The other two values on the other diagonal, they are the coefficients of the x to the first term. Okay, so we just discovered a negative 3 and a positive 4. So basically what we've done is we have figured out a way to break the problem's x term down into two other x terms that will work nicely with each other. After you have your information filled into the box, what we did is we factored across the rows and down the columns looking for things in common. Okay, so looking across the rows, we could see that our first row had an x in common, our bottom row had a 2 in common. Our first column had a 2x in common. Our right-hand column had a 3 in common. Now you notice that some of these values are positive and some of them are negative. Okay, and this basically has to do with the lead term of each row and the lead term of each column. If your lead term is a positive number, then your factor will be positive. If your lead term is a negative, then your factor will be negative. Now, if you take the results from that factorization, okay, coming across the rows, we found an x and a positive 2. We're going to put those in a binomial together as x plus 2. Coming down the columns, we found a 2x and a negative 3. We'll put them in a binomial together, 2x minus 3, and that is how the trinomial factors. Now, another form of factoring that we have not seen a ton of, but it's absolutely critical, is there are three very specific rules that apply to certain types of binomials that we may run across. And it's critical to do this because there is no method that you can find that is going to show you how to do these. These are simply factual. When you see the structure of these situations arise, then you have to know that this is how it factors, and it's memorization only. Okay, so one of the things that we looked at is, of course, the idea of a conjugate was needed, and a conjugate is simply a binomial and the exact same binomial where the only difference is the sign between the two terms in the binomial. So x plus y and x minus y are conjugates of each other. And that actually becomes important right here. The difference of two squares. Let's say you have a binomial where you're looking at it, and the first term is a perfect square, meaning you can take its square root and you end up with a nice, neat number, not some crazy, irrational decimal point. Okay, and the same is true of the trail term. Okay, so we have two perfect squares, in this case of the example, a squared minus b squared, but it could be 9, 27, 36, any of the perfect squares. Okay, that factors into a binomial times its conjugate, where you're looking at the square root of the lead term and the square root of the trail term as your lead and trail terms in both of those binomials. And there are several examples worked out in the notes from this day. Okay, the sum of two squares is actually prime. It is not factorable. Okay, so keep that one filed away. We also saw the sum of two cubes and the difference of two cubes. And again, same concept, but completely different formulas here. Okay, a cubed plus b cubed. Okay, so we have a perfect cube in each of those positions, in the lead term and the trail term, and that factors into a sum of the cube root of each of those two terms, and then that's multiplied by the cube root of the lead term squared minus the cube root of the lead term times the cube root of the trail term plus the cube root of the trail term squared. Now it sounds a whole lot worse to say that out loud than it actually does to work it out in a problem, so be sure to look at the examples if you've forgotten. And then the difference of two cubes works exactly the same way with a couple of sign changes in the structure of the factorization. Again, there's no cutesy methods here. These are facts. You must memorize them, or else you will see a problem or two from time to time that you will not be able to answer. That brought us to completing the square. I'm not going to spend nearly as much time now as we did back in the day working on completing the square, because this is a skill we've seen a bunch here lately, so hopefully we have the idea here. And of course, the completing the square method is the idea that the trinomial you're looking at will not factor into a binomial squared. So what we do is we blame the c term, we send it to the other side of the problem, and then we invent a new c term by taking half of our b value, okay, and squaring it. Whatever the result of this is, we must add it into both sides of our problem. Okay, the result of that will be that your trinomial now is factorable. It's a perfect square trinomial, and we can break that down into a binomial squared. So we take the square root of the lead term, we keep the sign of the middle term, and take the square root of the trail term, and that's how it factors. And again, look at the notes on this. Watch the video if you're having trouble with that. Now, the reason we were going to all this trouble is because of what the quadratic equation might do. Okay, in standard form, which is the ax squared plus bx plus c, okay, that is not very helpful when it comes time to graph the parabola, nor was it helpful when we were trying to graph any of the parent functions that we had. So what we'd like to do is we'd like to get to the vertex form, which is that y equals the x minus h quantity squared plus k, and h and k was the vertex of the parabola. This was the first time we started seeing this particular format. So the idea was, if you ran into standard form like you're looking at there and needed to know where the vertex of this parabola was, you could complete the square in order to get into vertex form, so you could actually find the location of the vertex by reading the equation. Okay, so that's how that worked. And then finally, lastly, okay, the structure of the parabolas. Okay, so we took a look really for the very first time and said, all right, we have a parent function, y equals x squared, and we expanded it into the y equals x minus h quantity squared plus k, where hk was our vertex. Okay, and we started actually first graphing the parabolas. Okay, so the parabola opens in the direction of the first dimensional variable. We've seen that here lately. The sign of the a coefficient will tell whether the parabola follows your positive or your negative axis. Okay, we've seen that as well. Our parent function value of a is 1. If you get a smaller coefficient, that's going to cause the graph to widen up. In other words, it's not rising or falling to infinity as fast as it should have. Larger values of a is going to make the parabola skinnier because it's speeding off to rising to or falling to positive infinity or negative infinity faster. It will have a line of symmetry that passes through the vertex going the same direction as the parabola is. And there's kind of a bunch of stuff that we learned about parabolas, but that is all we learned at this point. So obviously Unit 5 was gigantic. There was tons of stuff in it, so it worked to our benefit that we had to break it into 2 pieces. But anyway, there is your Unit 5 review.